Hi, I'm James McGuire, and today we're talking about continuous intelligence, which is another form, sort of the advanced next generation form of real-time analytics, kind of, it's actually more than that. To discuss the details, I'm joined by three major thought leaders. With me is Sam Ramji, Chief Strategy Officer at DataStax. Hello to you, Sam.
Hey, how are you doing? It's great to see you, James.
Good to have you with us. Also with me is Mr. Simon Crosby, Chief Technical Officer at Swim.ai. Hello to you, Simon.
Hello, James. Good to be here.
And Simon, you don't even work for a .com, you work for a .ai. That's very current, it's very 2020. We want to be hip today.
Yep, we got, and smart.
and good looking, if at all possible. We're going to work on all three of those.
Yeah, we need the zoos. Yeah.
Rounding out our panel is George Gilbert, industry analyst focusing on data management and analytics, formerly with Gartner. Hello to you, George.
Good to be with you.
Absolutely. So let's talk about continuous intelligence. I think, not everyone really knows what continuous intelligence is. I think it was, 451 Research said it's actually the top tech term of 2020, believe it or not. It's sort of a very next gen thing. So let's figure out what continuous intelligence is. I think it's like, faster than real-time analytics. It incorporates historical data in real time. It leverages artificial intelligence, to automate decision-making. George, if you succinctly define continuous intelligence, what would you add there?
I guess I would look at it as something where we need to inform or automate decisions continually. And I know I'm using the answer. I'm using a word from the definition in the answer.
In high school sociology class, you would be dinged for that, George. We would allow that. Yeah.
I would, but I think that it's a new approach where in the past, basically the data came from a database and informed something where, because we built things where we sort of stored them and analyzed them, reflected on them, there was a latency. And so even if you were doing things continuously, you were actually doing something where there was enough of a lag that it was closer to a sort of an offline decision. And here there's a continuum, and now the decisions need to be much closer to real time. And so therefore they need to be much nearer to the data that's triggering them if possible.
Mm-hmm. So Sam, what would you add to that? Continuous intelligence, if someone came up to you at a party and they knew something about technology, but not everything, how would you define continuous intelligence?
I'd say it picks up where continuous integration and continuous deployment left off, which is the next layer of the stack. How can we be constantly updating our decision models? Because what we don't want, exactly as George pointed out, is a fake real-time learning system that is really a batch behind the curtain, right? Don't look behind the curtain. They're just doing a batch upgrade on the model once a day. And so you're only getting smarter in increments of a day. So the competitive basis of CI/CD was that you could shift features around and change your understanding of your engagement with your users, really deployment by deployment. And you could push to production in minutes to hours. So you should be able to do multiple deploys per day. When you bring that to what we want to see in automated intelligence in our systems, how can this application learn from all the behaviors of all of its users? How are those things moving? And how can you do that within a bounded context that doesn't require yet another loop of human data scientists and model builders to make those incremental adjustments?
Mm-hmm. So, Simon, what would you add in terms of, I haven't heard the word artificial intelligence yet. I'm going to guess that AI and ML are certainly a part of this process.
So these are applications that always have to have an answer. So you can't afford to wait. You can't compute when a human looks or when a GUI wants to refresh. You always need the answer. So if there's a pedestrian crossing a road, you got to know, right? So this notion of needing an answer means that data has to drive computation. And so when data is generated by sensors, you've got to compute and analyze that and do the AI on the fly so you have an answer. And so data drives the whole computational process as opposed to humans with SQL queries or whatever. Mm-hmm. So, and that's a fundamental change. It's a big change, by the way. In the normal AI world, we have a data scientist who sits and builds a model in the cloud, trains it, and then pushes it maybe to the edge or does something. Here, we have to continuously learn and predict. Mm-hmm. And that's quite a change.
I think this is a super keen insight, and it's a really nice framing, because if you can't quite put continuous intelligence into your dinner party conversation, you can say data-driven applications. And if we understand that it's the kind of fundamental shift that Simon's pointing at, then you're starting to move in the right direction, right? That's the core of it. Data-driven applications.
There are some other cool things that really make this possible.
All right.
And that is that we've seen huge advances in big memory computers. You know, there are huge things out there with terabytes of memory. And so we can afford to keep everything in memory and run at CPU memory speed instead of disk speed. So in the cloud, we're sitting at, you're sitting behind 10 milliseconds or whatever to get to the database and back. That's 1,000,000 times slower than doing it on the CPU. Wow. That's horrendous, right? It's 1,000,000 times slower.
Yeah, you have to look at Jeff Dean's list of numbers every computer scientist should know, and then you can really kind of get into the mind that Simon is offering you, right? To say, like, what is speed, and when you say, well, this is 6-7 orders of magnitude different, then you can start to understand where different types of computation ought to be happening.
Yeah.
Well, if we ask, what is the advantage? It seems like the obvious advantage is it simply goes faster, and the world is going faster. We're dealing with more data all the time. So I'm guessing that the answer to what is the advantage is more than just it's faster than ever before. George, what's really the advantage for businesses for continuous intelligence?
Well, there's a premium on how fast you can inform or automate a decision. And I guess if I had to sort of distill it down to that would be the most basic thing. That there's also there's also a skills issue, which I think we've alluded to, where what was going on in the cloud with cloud native architectures really was a way to do scale out for what was formerly scale up, but it still took a huge amount of skills to program that distributed architecture. And a benefit to businesses is beyond just making the decisions faster or informing the decisions faster, is that you now need to be able to build these applications closer to where the skills of operations technologists are becoming involved, as opposed to the information technologists. And so that requires a simplicity, a much more sort of end-to-end vertically integrated set of application and infrastructure components that can figure out where to distribute themselves, but also how to maintain all the application components, so that when one change happens in one place, it knows where all the other components need to be updated.
So skills efficiency, I think, is the point you're making, George, and I don't disagree. But I think there's a bigger outcome-based answer to where James is going, and I guess I would use an example of the Home Depot in 2020, right? So we've got a company that's functioning extremely well. They're doing a lot of modernization, and then they're a retail company, and all of a sudden you have COVID and people aren't going into the stores. Well, you don't have to be a genius to know that people tend to buy more when they go and see things they need. And if they're not seeing things that they need, then that's a business outage. So they adapted their systems and built what I would say is a continuous intelligence application for curbside pickup, which gave you the same basket upsell, right? It gave you the same expert interaction to say, hey, from the things that you're building, Bob, it seems like you're building a garden shed. Do you have do you have this kind of wrench? Do you have these kind of fasteners? It's funny, I don't. Oh, hey, well, we'll get those for you. But the customer's sitting there waiting at the curb. So how patient are they going to be? So they built an application that would dynamically dispatch, right, the expert advice from the person who's meeting the customer at the curb. into the big box store to the associates that are walking around serving other needs at the same time and saying like, hey, you're in this aisle, pick that, you're in this aisle, pick that. And you got 20 cars waiting in the front. So it's a dynamic dispatching problem. It's a fascinating problem. And it requires you to have a combination of knowledge of what's in the store. You need to have cloud-based intelligence of what are the patterns that you typically see across all of the Home Depot environments, times what's actually available right then. So that actually showed up in Home Depot's revenues, right? They had double-digit revenue improvements and margin improvements during the COVID recovery. So those kinds of responses make businesses smart, and smart businesses are successful. The ones that can't adapt actually fade out. So those are the outcomes that I'd look, despite the fact that George and Simon and I are all, huge tech nerds, and we would love to talk to you about, cloud edge device architectures and,
Sure. We should
microsecond
get to
memory,
that.
Memory gates, right? But that's what it's got to be about, right? How are you changing the
Yeah,
customer's
we'll get there.
expectation and the business?
But one point about the Home Depot example, which I think is really interesting, is that these requests are coming in real time and they need to be fielded really fast. But of course, they need to be fielded. They need to be married to the historical data of like, what are you going to need to build that shed? You're going to need the wood. You're going to need the screwdriver, et cetera, et cetera. So it's got to be new, fresh, real-time data, but it's got to be accessing the historical data at the same time.
Right. It's adaptive decisioning.
Mm-hmm. Interesting.
Yeah.
Simon,
By the
something
way,
you'd add about an advantage, please? Yes.
So do you like blueberry muffins?
I love blueberry muffins.
Okay. By the way, you didn't have to phone your mom to find out. You figured it out yourself,
She makes a great blueberry pie, by the way, but she does not use data analytics to make her pie. But please.
Good for you, Mrs. McGuire. But anyway, or whatever her name is. But
Mrs. McGuire.
So here's the thing, right? So you learned yourself, and so there's a really cool thing in at least our approach to continuous intelligence, which is that if you take a stable computational approach, then things can learn for themselves. Okay, so I'll give you an example in SWIM's continuous intelligence from traffic infrastructure in cities. Digital twins, smart digital twins, I guess, of intersections learn from their own data and their neighbors, and they predict their future. And they stream it. So they can predict their own future. So they can learn based on what they see. And so if you take the stateful approach to computing on data from things, then these stateful representations of things, which in SWIM are called web agents, can learn and predict for themselves. They can continuously learn and predict for themselves. And that lets you have a much more simpler data-driven model. Let me make that very clear. As opposed to having a model of a city built by a data scientist who has to train the model with data, we have a much simpler approach where little computational representations of things, these kind of smart digital twins, learn and predict for themselves based on their own data.
Are you saying like a traffic light or some other element of that smart city is going to learn itself, so to speak, over the course of time?
I'm not saying the light.
Okay.
People always get confused with the where does this stuff run? It actually probably runs in the cloud mostly. But the digital representation of the thing,
twin,
right? Yeah, a digital twin runs someplace, processes raw data, and it analyzes, learns, and predicts. And if you can do this at scale, probably most applications are hybrid in the sense they span from some on-prem source of data to the cloud, which is where most of these things will run.
Yeah, it's kind of like, if you think about how we grew up programming, right? Procedurally based and then object oriented. This is kind of the opposite. It's like taking that and standing on your head. It's more like agent environment, right? Yeah. You have autonomous agents that are not brilliant, but they're smart enough to be themselves. And then the intelligence of the system is actually the emergent behaviors of all of the agents, right? In those environments, or what we might call bounded contexts. It's super clever. And what's really interesting about it, as George was saying, we kind of built a mainframe in the sky, right? That's a cloud. And then the way that we scale things is usually stateless applications.
Yeah.
Right. We've got procedurally based applications or object-oriented applications that are communicating at scale through a database in order to access their information so that you can scale them horizontally, statelessly. But the state's got to be somewhere, right? Like, where's the state? And with I think what Simon's pointing at is in a data-driven application, one model you could take is what he's taken with Swim around the sort of agent environment approach. Is that fair, Simon?
Yeah, it's perfect. Actually, REST and databases are fabulous because it allows us to scale a cloud, but also the statelessness means that the application at the front end has to only update the database. So it also comes into this interesting discussion, which I wanted to get into with you, which is, can a database deal with this, right? Can smarter databases do this stuff? And that would be a good discussion to get into.
And Sam, I definitely want to ask you that question. Before I do, let me thank the people who are watching and listening. Thank you so much. And we welcome your questions. You don't have to wait until the end. You can ask a question anytime. Rusty, Matthew, Heather, please, we welcome your questions. There's the Q&A box at the bottom of the screen. Ask us anything. We are fearless. It's Sam, in the meantime, please, what is the answer? With all these data streams going every which way, can databases keep up with it all?
I think old-fashioned databases can't, right? And so one of the things that we're seeing is, if you just want to look at gross measurements of economic activity, right? You can look at market behavior, right? So SQL databases, classical single instance, and in some cases replicated, but usually you don't think replication, you think scale up. That market is about $45 billion last year. It's growing about 14%, which is pretty fast for a market that size. Whereas non-SQL databases were about $6.5 billion last year, but they're growing at 45%. Right, but obviously law of large numbers and small numbers, right? That 45% growth will fade, right? But IDC thinks that that's going to end up at about $22 billion by 2023. So that's just a sign that a new form of computation is coming in extremely quickly, and it doesn't look like single instance databases, right? I think all single instance database technology is archaic. It's legacy. It
but also
the
traditional, Sam, the traditional relational model is kind of archaic, right? Yeah, yes. Buses have engines, but the bus is nearing the stop. That's a different thing, right?
Right. Everything that we care about in data is related, right? It's got a relationship of some kind that is often best described in a graph. It's spatial and it's temporal, right? Those are the three basic laws of data. So when you start looking at where databases are going, I'm not sure it's really even fair to call what we're now building databases. They're more like data fabrics, right? It's a network of nodes that look more like what we used to think of as being massively parallel computing, but in a consumerized, right, sort of mainstream, to George's excellent point, right, something that operational teams can actually make happen before the heat death of the universe and without spending their entire annual budget.
Right. We're just coming any day now, right?
Right. Well, so that's kind of what we see, right? Is these massively distributed environments. Look at what Google used to build multiple new billion-dollar businesses per year, right? They built that on Spanner, right? And then they analyzed the data through Bigtable, right? And so when you look at what that built along with Borg, you've got kind of, Google is a continuous intelligence company. That's how they've achieved their revenue, their growth, and their ability to spawn off new enormous businesses. So when we back it off, is there a future for a classical Oracle or SQL Server databases? The future is the past, right? It's continuing to run the things that have been built. But if you're building new things on old databases now, you're kind of dead on arrival because the data needs to be much lighter. It needs to have much more intelligent replication. You can't afford to replicate all the data that you care about. That would be foolish. Yeah. So the right parts of it need to live where it needs to be, and that needs to be able to migrate in a fluid fashion.
But on that same note, just a quick one, if I can. Say, when you talk about some of the legacy database players, this week we just need to use the word Snowflake at least once because it is this particular week. If we don't use the word Snowflake this week, we're out of it. So, is Snowflake up with 2020? I mean, that must be. What is Snowflake equipped to keep up with the world that you're talking about?
So one of the things that we should have enormous respect for is that everything that we talk about today is really about the application experience. And so what we've talked about so far really is, it's the fast path, right? It's the application plane. And it's easy to get our heads wrapped up in that and think it's the only thing ever. But that would take us away from all of the data warehousing, all of the slow path, but highly intelligent discovery, right? So when you look at Snowflake's innovation, really looking at Hadoop as a pioneer species that went in and created a lot of new thinking and new ground for scale out data warehousing, being able to have a product that really just works and an engagement model that that can take all that data still needs to be used, because typically the things that we do to make operational databases perform make them relatively expensive to store all the data in the universe. Like if you're writing a terabyte a day to your operational database, you're probably not going to use that same infrastructure to store exabytes. Probably your economic cost basis is different, right? Yep. So you're always going to have some distinction between what's worth having hot and then what is worth remembering so that you can become intelligent about it. So I think Snowflake has got great upside there.
Yeah,
right.
That's the big legs. And I think there's difference between different classes of applications. So by way of just an example, we do a ton of work in Dubai on traffic. So if a truck with bad braking behavior is approaching an inspector on the street, tell the inspector. Okay, so every single moment you have to continuously evaluate whether the truck has bad braking behavior and whether it is approaching an inspector. And you can't tell the inspector too late, because otherwise what's the point? And every inspector just wants to know about their local truck. They don't want to know about other ones, right? So this notion of, solving these continuous problems at scale meaning every inspector and every truck in every city, is the category that we're interested in.
To sort of dwell on some of the challenges involved with continuous intelligence, Georgia, you have this interesting idea I want to follow up on. You sent this in. We may have touched on this a little bit, but I think it's worth digging into. Continuous intelligence, you said, inevitably has to scale to levels cloud-native architectures can't handle. So how can continuous intelligence applications maintain simplicity for developers and administrators that would otherwise be crushed by a cloud-native approach? Cloud native, of course, is very current and very sexy, but you're saying that it really can't even keep up with it, with the concept. What is your take on that?
All right. I'm getting ready for this. Now it's
going to get juicy.
All right, George, go for it.
I think one way to look at it is that there's a continuum. When you've got a cloud native architecture, you're supplying sort of the developer and the administrators are supplying some intelligence sort of explicitly about how to put all the pieces together, because you have specialized pieces that are good for specific functionality, but then you have to say, okay, here's what data is going to stream in, here's how I'm going to persist it, here's how I'm going to prepare it and analyze it, how it's going to inform a decision. But when you're closer to the edge and you've got, many orders of magnitude more entities that are supplying data that need to get informed about decisions, something's got to tie all those pieces together in a way that would be probably much more difficult to be done manually. Like at a sort of one simple example might be, streaming sort of raw telemetry in preparing and enriching that data, knowing what metrics need to be updated, then knowing where that analysis needs to go and what models need to be run inference to inform a decision. It's sort of like this whole fabric of things. Someone needs to automatically update all this without sort of explicitly coding it, if possible, because you've got perhaps millions of entities that are interacting. But then it's also, how do you operate this thing? So someone is, or something has to be looking at how this is laid out sort of logically or physically and how it's behaving, and to tune all this And I think what works in a cloud native architecture might need to be sort of simplified, sort of where you've got some automagical intelligence when you've got orders of magnitude greater scale, sort of out closer to the edge. And again, I'm supplying sort of a technical perspective on it, but I think the approach just is probably going to be different when you're at that greater scale than when you did the sort of scale out approach of a scale up architecture that was in the cloud.
We have such a fundamental disagreement on this topic that I have to wonder, how do you define cloud native? What does that mean to you?
I guess I'm thinking of it as where you've got infrastructure that provides a way to transport data and gives you ways to sort of publish and subscribe to different elements of that data, ways to persist it, then ways to analyze it or prepare it and analyze it, and then ways to inform or automate a decision, but that the components are things that we're familiar with. I should say, the artifacts are familiar things, like what might have been originally an enterprise service bus, now becomes a stream processor. What was a SQL database now could be something scale out, like a wide column or a document database. And what was using a data scientist to train a model and then a data engineer to deploy that, or an ML ops engineer to deploy that these were all artifacts that were, I guess I'm thinking of as appropriate in the cloud, but that when you've got 1,000 or 10,000 or 100,000 more elements, that you need a sort of a simplified approach.
So my bias here comes from a different definition of cloud native at root, which is Kubernetes. Right. So when I think cloud native, I'm not talking about Amazon's definition of cloud native, which is use our 1,400 APIs, right? But a Kubernetes basis, right? Because now you've got a compute fabric that you can put anywhere. So when we talk about cloud native strictly, we don't mean what you said. We actually mean a fully automatable environment that does not require manual intervention, that is highly programmatic and algorithmic in its best cases, and can be laid down in a hybrid plane, something that can run just as well on Google Kubernetes engine or Elastic Kubernetes services or Azure Kubernetes services as it can on OpenShift or Tanzu running on-prem. So what I see is the opposite of what you're saying, George, which is that you can actually have a common programming model, you have a common packaging mechanism of Helm charts and CRDs and containers being deployed on Kubernetes into Dell hardware on premises doing last mile edge computing. And the scalability of that is extreme, because it's like you can scale out and out and out and out. You can scale down to the edge, and the entire thing can be automatable because there's also common telemetry using models, as open and simple as Prometheus to things that are more complicated that you see in open source IoT edge gateways, which is one thing that we will use to aggregate, right, these thousands of different feeds. And this, in fact, is the model that we see, for example, at GE Aviation, where they actually have to test jet engines, and then they have to predict all of their behavior characteristics because they no longer sell jet engines. So going back to the outcome of continuous intelligence, James,
they rent them.
They sell power, they sell uptime, they sell availability.
Yeah.
Right. So it's their ability to model the 10,000 different sensors on a modern next generation jet engine in real time, take all that information, make a U-turn and put it back in a UI for the test engineers within 10 seconds. Because if it overheats, it could explode and then people will die. But once they've got that model at high fidelity of all of those performance characteristics, that becomes the digital twin. So they ship that, and that is how they manage their business.
Sam, let me just ask, I just want to, I think I understand what you're getting at, but then there might be, I might be approaching the explanation sort of from the wrong angle, but I think there's a common element that may complement what you're getting at, which is that there's a knowledge of the application model. And by model, I'm not thinking of the sort of the container and how it's distributed
Right.
and managed, but I'm thinking about
Getting application down.
yeah.
Yeah. So I have an example of that. And start with the answer. The answer is similar to data build the app. So the application is connection quality optimization for a mobile carrier, where we have more than 100 million devices out there and tens of thousands of base stations, and every one of these mobile devices has a smart digital twin which continually predicts where it's going to be, so we know where they're thinking they're going to go, and we know how to balance connectivity of the whole network for all of the devices and so on. Now, that is potentially a massive application, but the application developer has to do a very simple thing, which is just pretend that they're a mobile device and work out how to process their own data and define where they're going, right? So that learning is very simple. It's where was I yesterday and where am I going to be? And the application, which is proximity of users to mobile device to base stations, is pretty straightforward. So the application itself is only a few thousand lines of code, but at runtime, it naturally distributes over Kubernetes-based infrastructure to 40 or 50 nodes to do continuous computation and to stream results.
Would it be fair to say, I just want to see if I can square that circle. Would it be fair to say that when you're talking about like a Kubernetes-based architecture, you're talking about a operational model, and then what Simon you're talking about is sort of the application model, where you're modeling some very simple entities, but you've got hundreds of millions of them, and the application fabric takes care of sort of all the connections and intelligence. Would that?
I think that's entirely fair, right? Because Kubernetes is very much a operational framework, right? An operational environment for large-scale automation to make things feel like clouds, right? Whereas Simon is talking about an application programming model. But I think in the case of Swim, Simon will be much more articulate about this than I will. I think there's a underlying infrastructure that is assumed to come with the application model that takes care of some of those.
Oh, we deploy on some number of instances on Kubernetes, and the instances hook up in a mesh. So I absolutely agree with you. And I think hybrid is the way to go. All the smart cities work we do, the data is coming out of a city. It's coming out of a spigot, so Las Vegas is 60 terabytes a day. And so the processing to move from data to state is happening at the physical edge, but the learning inference is happening in the cloud on a GPU attached instance in Azure. So a hybrid deployment makes sense often.
And one of the key things that I think the Home Depot case, as well as the Smart Cities case, point at, and the GE case, is you have to assume that the future is that everything needs to have some kind of connection, but there's going to be a lot of weakly connected computing. We used to talk about OCC, occasionally connected computing.
Yeah, that's right.
I think we're going to see a lot of WCC, right? It's just you're often going to have like a thin pipe, and then then you might have better connectivity, and you have to do really, really smart things while you're weakly connected. So this is an architectural disjunction that we couldn't really figure out how to do until more recently, as we're seeing the innovations from from Google and from VMware, right, from startups, like the ones represented here, to figure out how do you take an application model that's consistent and an operational model that's consistent and blanket it everywhere to solve all these problems, rather than siloing, right, your application and operation stack based on, right, these non-functional requirements, right? How do I, um, you know, how do I do just this one thing? Does that make sense?
It does. And I want to ask, before I go to that, one last question about the future, I want to ask something about the cloud native disagreement. Down at the simple level where I live, if you could clarify one thing for me, it's that I think there's all these IT administrators out there who are thinking about cloud native. They're working with some of these legacy things. It's kind of like lift and shift, or they're trying to, but then people say to them, oh no, it's got to be cloud natives. It's actually literally built for the cloud. So that's what I think about cloud native. That's what that's about. So what is my simplistic understanding? Where is the disagreement between, say, yourself and George versus my very simplistic understanding of what is cloud native?
I think your simplistic understanding is pretty much right on. The difference is when George was talking about his point of view, he was expressing cloud computing,
Okay.
which is bounded to one of the hyperscalers and
Yes.
building in one of those. And right, that is clearly correct, right? You're not going to do the kinds of continuous intelligence end to end, edge connected and
because they're
computation
fundamentally
on that model because they're limited, right?
for rest and legacy databases. Yeah.
Whereas cloud native says, okay, we want everything to have that same set of affordances, right? How do you think about the fluidity of that stuff, but be able to take it where the providers don't exist?
Maybe,
Gotcha.
maybe,
Please.
and this is between Simon and Sam. If I can sort of extend that, if the cloud native allows you to take that sort of operational model from the cloud and extend that beyond that, maybe then the way to express the connection to continuous intelligence is that we need a new application model that complements that. And that's what we've also been talking about, which is where you've got this sort of, I guess, application fabric that is sort of much more seamlessly distributed and sort of has enough intelligence built in that you don't have to have the entire application architecture in your head. You put little bits of intelligence where appropriate, and this fabric then figures out how everything runs.
Yeah, I totally agree. There's a composting process for every new way that we do applications. There's a model, and then there's a framework, and there's a platform, right? So you think like there was a model, hey, we're going to do model view controller, and then there was a framework, Ruby on Rails, and there was a platform, Heroku. Right? You can find this over and over again in the history of computing and computer markets. So yeah, we don't have a great consistency around the model, and people are doing a lot of bespoke custom work on how to do continuous intelligence and data-driven applications. It's kind of artisanal right now, but I think Simon's going to help bring that forward into the industrial phase.
So
let's look at the future. In terms of us running out of time, I hate to take too much of you guys' time. If we look to the future, if we're going to have this conversation 2 or 3 years from now, we're talking about continuous intelligence, which I think is really, it's all about edge computing. I'm surprised I haven't heard more of the phrase edge. I think we have some of it, but Simon, what are we talking about if we talk about this subject 24 months from now?
So just with regard to edge, the edge is not a place. The edge is not a place. It's where we get to process data. Okay, and often it will be at the physical edge. Sometimes it'll be in the cloud because you won't know where the source of data is, right? It'll just be the internet. Okay, so there is one key benefit that we haven't touched on, and that is that once you adopt the stateful application model, you can do data science on live data, which is totally trippy. It flips people out, right? I can run PyTorch on 100 million web agents, live digital twins of things out there, real people and their mobile devices, and I can figure out the optimal way to solve another interesting problem for my enterprise. And so this notion of batch mode processing, so store then analyze, changes into one which is analyze and react, which is really, really powerful for any organization.
Right. It feels like it's going to be the default choice in the years ahead. George, your take on the future of continuous intelligence? What are we going to be talking about in a few years?
I actually think Sam distilled it in a way that sort of makes all the pieces kind of fit together, where he says, the sort of the model, the framework, and the platform, if I'm capturing that, right, and that we have seen, like, Simon and Swim put together what sure seems like a very sort of elegant implementation of all three of those, and it's going to sort of be a pioneer that's, I guess we'll see other implementations. And I think what the cloud vendors are trying to do is potentially sort of, as their platforms, sort of the water level rises and their abstraction level rises, like when they add an application mesh, I mean, I think they're trying to start adding that sort of distributed intelligence that sort of holds more of the pieces together transparently. What I don't know is, can they really bring along all the baggage that they've got, where a fresh implementation makes it, so much simpler.
Mm-hmm. Mm-hmm. So, Sam, your take, the future of continuous intelligence? It sounds pretty wild.
Yeah, well, I think it's been well summarized already. I'll add two things that I think are material. One, I think distributed data is going to be much easier in 3 years, because we will have solved for laying out distributed data on Kubernetes. So the parallel effort, right, that's been running for a while to re-platform the enterprise on Kubernetes will give us a standardized control plane for laying out data and doing intelligent replication, which is going to be, right, the infrastructural component that application frameworks and platforms like Swim will rely on. I think the second thing, and this is maybe the one to grow on, the less obvious one, is this is going to create a real wave of auto ML. When we talk about data science, we're talking about a desperately labor-locked market, right? There's demand for 3 to 4 times as many data scientists as there are in the world, or as there are likely to be produced.
Right.
So in those kinds of environments, you could do one of two things. You could either make the data scientists more productive, or you could make other people more like data scientists. So when you listen to Simon talking about being able to do data science on live data, lots and lots of engineers, I mean real world engineers, not like software engineers, right? Like, mechanical engineers, construction folks, right, will be able to look at these things. They're domain experts. They'll have access to data. The data will be well governed. And then they'll be able to use auto ML almost like a microscope or an oscilloscope, and be like, hey, I think there's some interesting dimensionality. There might be a feature in here. And as they discover it, then they may hand that off to the data scientist. Or, right, there might be enough value in the model, they might hand that right back into production, right, through this framework platform mechanism. So I think distributed data will be available and easy, and auto ML will be prevalent.
That's right.
One of our viewers, Rusty, has a really interesting question. Actually, I think it's very germane. He asks, has 5G had an impact on continuous intelligence? I would rephrase it and say, will 5G have an impact on continuous intelligence? Sam, what's your take on that?
I will be surprised if we can really execute 5G without it.
Right.
Because one of the things that most people don't understand about 5G is that there's not a tower. Right. In my neighborhood, there's a movement afoot, like, don't let them get into a 5G tower in here. I'm like, do you know what this word means? I do not think it means what you think it means. But 5G is such an interesting technology. It's such a weak mesh of radios that it can't even penetrate a building. Right. Like, getting a signal inside a building with 5G is super hard. So what does that mean? You've decomposed a classical tower into a whole bunch of small radios that have a lot more capability but less range. Those things are also breaking all the time. People are moving all the time, right? So how are you going to model that incredibly decoherent physical environment where you've got untrustworthy infrastructure, things can break, and you still have to have a trustworthy signal to that device so that you can get location-based services, so that the killer apps work, and so you can make a phone call, right? So all of these things really kind of have to sit together.
And they're promising, secure quality of service-based services to enterprises, which is even more than that.
So it requires intelligence. I had the privilege of speaking with Toby Redshaw at Verizon a couple of months ago, and he made a really, really interesting statement, because they're really one of the best intelligence companies out there. They've got like a 5,000 server strong farm of Hadoop, probably the best managed, most performant Hadoop in the
Verizon you're
world.
talking about?
This is Verizon.
Oh, okay.
And he said 5G is about 40 times more AI intensive than 4G. And this is what he was talking about, right?
Okay.
This kind of factor.
Huh. It's going to be interesting. I thank the three of you for sharing your expertise. Absolutely. I think the three of you are truly technology philosophers. You guys are deep, to be sure. I've learned a ton. Thank you very much today.
Thank you.
All right.
Thank you, James. Thank you, George. Thank you, Simon.
Yep. I will send you guys the link when we're done, when it's edited. Thank you very much. Take care.
Hey, thanks, guys, for showing up. I really appreciate it.
Awesome.
Absolutely.
Thanks.